Hi, in this last video on electrophilic aromatic substitution, I'm going to discuss activating and deactivating groups and the role that they play in the Regio selectivity of your aromatic compounds. So the first thing I want to take note of is what the different positions on the ring are called, because this nomenclature is going to be important moving forward with the rest of this video. So let's say I have toluene. Draw a better methyl group on there. There's three different positions. Position 1 here in orange is called the ortho position. Position 2 in green is the meta. And then position 3 is para. And this is all referring to these positions with respect to the toluene group. So ortho, meta, and para. So these terms you'll need to know for how the activating groups and deactivating groups direct new substituents onto the ring. So first up is activating groups. So activating groups donate electron density into the ring. And given the ring acts as a nucleophile in these reactions, that increases reactivity. So there are three categories of activating groups: weakly activating, moderate, and then strong activators. So for weak, this would be alkyl groups. So a methyl group or an ethyl group, they donate electron density through hyperconjugation, but that's not very strong. Next up would be the moderate activators. The main two to think of here is a methoxy group. That would be a moderate activator. And then a group like the one in this compound, where I have an oxygen that has lone pairs next to the ring, but then that oxygen is also bonded to a carbonyl group. So the oxygen can both donate electron density into the ring, but also this carbonyl group is pulling some electron density towards it. So that's what makes it moderate as an activator. Then a strong activator is going to be a compound that has a delocalized electron pair adjacent to the ring. So a hydroxyl group. Or any sort of amine, primary, secondary, or tertiary. So if we do an amine, for example, I can draw the resonance structure of it donating electron density into the ring. So now I have that lone pair, and then that can be delocalized throughout the ring system. So all of these activating groups are always OrthoPara Directors. And I'll go through an example here to show you what that means and why they're OrthoPara Directors. So let's say I have phenol. And I am adding a nitro group on. So if you remember the conditions, we just have nitric acid and sulfuric acid. Let's say first I add the nitro group to the ortho position. So if I do that, I'm going to have the NO2 group there, and then my carbocation right there. The hydroxyl group can donate electron density to that carbocation. And now I no longer have a carbocation anymore. So that's what makes it an ortho director, because the carbocation can end up on the carbon adjacent to the electron donating group. Similarly, if I were to add to the para position, adding a nitro group, I would get what my nitro group here, and then my carbocation right there. I can draw a resonance structure where now the carbocation ends up on the carbon adjacent to the hydroxyl group. And then, of course, I can draw a resonance structure where the oxygen donates that electron density to get rid of the carbocation. So in both these cases, that electron donating group, the activating group, is stabilizing the carbocation intermediate by donating electron density to it. If I were to add to the meta position, using the same set of reactants I had before, I would get this. So I'd have an NO2 group here. My carbocation would be right there. Draw a resonance structure here. And my carbocation now is on that carbon. If I draw a resonance structure again, the carbocation moves to the other ortho position. The problem is I never get my carbocation on the carbon adjacent to the hydroxyl group. So this intermediate is higher in energy than for either the ortho or the para addition. So that's why these activators are OrthoPara directors. Now, compounds can add to the ortho or the para position, so you may get multiple products. So if I have toluene, and say I'm going to add a bromide to it, so I have my iron bromide as the Lewis acid catalyst, I could get multiple products. I could add to the ortho, and I could add to the para. So you will get both. Probably the para is going to be more common than the ortho just because of steric interactions, right? Para positions further away from the methyl group. And especially if the methyl group was a larger alkyl group, then you would have more para product, right? So say I have a reaction here with toluene, but now I have this tert-butyl group on as well. I'm adding the bromide on. There's 3 positions I could add to. 1, 2, or 3. I'm going to add to the ortho position that's not next to that tert-butyl group, because this is a large group that's going to sterically affect both that position and that position. So this ortho position would be heavily favored in the reaction just because of steric interference. Now, if I have two different activating groups on a ring, the stronger is going to dictate the Regio selectivity that I get. So say I have this compound where I have a phenol, so that hydroxyl group, and then a methyl group. And I'm reacting it with bromide. I'm going to add to the ortho position to the hydroxyl group because it is the stronger activator. So this would be my product. I'm not going to add to this position because that would be meta to the hydroxyl group. And given the hydroxyl group is the stronger of the two activating groups, I'm going to add to the position ortho to the hydroxyl. Now next up is deactivating groups. Like their name suggests, they withdraw electron density from ring. And this makes the ring less reactive. So what are your deactivating groups going to be? So your weak are going to be halides. So chloride, bromide, that's going to be a weak deactivating group. Moderate would include many carbonyl groups that are close to the ring because they can withdraw the electron density through resonance. So a ketone, right? Ketone, aldehyde, ester, any of those. Amide. Also think maybe something that can do it through inductive effects. That would have strong inductive effects. So a nitro group or a nitrile group. Then your strong deactivating groups, the most common one is going to be an NO2 nitro group because one, through resonance, it can take away electron density, but also nitrogen and oxygens are both very electronegative, so inductive effects are strong with the nitro group as well. Another good example of inductive effects that are taking it away would be a tertiary nitrogen, or I guess quaternary in this case, right? Its inductive effects are taking electron density away from the ring. Another induction would be a carbon that's bonded to 3 halide groups. Again, through inductive effects, it's going to take away electron density. Now, most deactivators are meta directors. So it's for the same reason that the activating groups were OrthoPara directors. Remember, if I add to the meta position, so now I'm putting in a deactivating group. If I add to the meta position, my carbocation will never end up next or on the carbon adjacent to the substituent. In this case, the substituent is an electron withdrawing group. So the meta position is more stable because my carbocation, which has very little electron density, given it's a cation, is never next to the group that withdraws electron density. Right? Imagine the electron withdrawing group trying to take away electron density from a carbon that already has very little electron density because it's a carbocation. It would be incredibly unstable. So the meta position avoids ever having that carbocation on the carbon adjacent to the electron withdrawing group. So the deactivators are meta directors then. Now the one exception is that halides are OrthoPara directors, even though they're deactivating groups. Right, here's why. So they're deactivating groups because they have strong inductive effects, given that they're electronegative. However, they also have resonance. So if I were to add to the ortho position, let's say, I can draw a resonance structure in which my carbocation will now be adjacent on the carbon adjacent to the bromide. This bromide can donate electron density, and I can get a resonance structure where I no longer have the carbocation. So that's why the halides are OrthoPara directors, even though they are deactivating. Just a couple more notes to finish off the activating, deactivating groups. So adding an activating group to a ring can lead to multiple additions. So let's say I start off here with just benzene. And I add an ethyl group on. My product is likely going to be this guy that has 2 alkyl groups added on. Because remember, once we add one alkyl group, an alkyl group is an activating group, so it's going to make the ring more reactive. So then I would add a second group on. The other one is reactions that contain activating and deactivating groups. So let's say I have a methyl group and a nitro group. I could get 2 products here. Since the nitro group is a meta director and the methyl group is a para director, I'll likely get, or it's an orthopara director, I can get one added to the para position here, because that's also meta to the nitro group. And I could get addition to the group, or to the spot ortho to the methyl group. Right, in both cases, it's meta to the nitro group and either ortho or para to the methyl group, which is an activating group.